So consider a collision in which, in addition to momentum being conserved, kinetic energy is also conserved. And so in this equation, in this problem, I'd have P final equals P initial, or if there were just two objects, I could say P1 final plus P2 final equals P1 initial plus P2 initial, or I could say M1 V1 final plus M2 V2 final equals M1 V1 initial plus M2 V2 initial. That's sort of the standard way of approaching a problem for conservation of momentum. But in elastic collisions, in addition to conservation of momentum, you get conservation of kinetic energy. And so you also have final kinetic energy equals the initial kinetic energy. And as I've said before, this doesn't have to be true. This has to be true if the system is isolated, if there are no external forces acting. This does not have to be true. This is only true when there isn't much energy loss in the collisions, like billiard balls, or if you play pool, things that are super bouncy atoms in the air. Those, the cart demonstration where they're interacting through the magnets, those are pretty close to elastic collisions. And so I can just write this one out, and I can say this is KE1 final plus KE2 final equals KE1 initial plus KE2 initial. And this one says, I can break these guys down the way I broke those down. This is 1/2 M1 V1 initial squared plus, V1 final squared plus 1/2 M2 V2 final squared equals 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared. And so now I would have two equations that I could use to solve my problem instead of one. Notice, by the way, all the halves would cancel out. And so you can combine these equations. And so I'll look at just a special case. If we look at the case where V2 initial equals 0, in other words, one of the objects starts out at rest, you can simplify these two equations a little bit and come up with some final equations. And so I'll sort of lay that out for you. You know, suppose we know M1, M2, V1 initial, V2 initial. So if we're given the two masses, if we know the two masses that are colliding and we know their initial velocities, this is the way scientists set up collision experiments, is they arrange it so that they know the initial velocities and the initial masses, and then they're looking for the final velocities. And so this would give us, you know, out of all these equations, we would know the m's and the initial velocities, and we would be looking for the final velocities. And if you remember your algebra a little bit, if we have two equations, this is equation 1 and this is equation 2, and two unknowns, you can solve for those. And so, I'm not going to go through the algebra of solving these for the case where V2 initial is equal to 0, but I'm going to write down what those solutions are. So the final velocity of object 1 is m1 minus m2 over m1 plus m2 times v1 initial. The final velocity of object 2 is 2m1 over m1 plus m2 times v1 initial. Let me just give you an example of this. So rather than derive these things, which would involve a bunch of algebra, I'm going to just check these things on a few cases. Consider if you look at the videos we did with the carts rolling, the case where m1 is equal to m2, right? That was the case where and when we were doing elastics, so they had the magnets. That was the case where I rolled this cart in, and the first cart stopped, the one that came in stopped, and the second one went off with about the initial velocity, about the same velocity as the first one had initially. And so, if you assume m1 is equal to m2, then v1 final is equal to m1 minus m2 over m1 plus m2 times v1 initial. But if m1 is equal to m2, then these two are equal, and that's just 0. And that's what we got when we rolled the cart in. So let me just see if I can do them all here. Just this won't work very well, but it'll work a little bit. So if I leave one cart here like this, and I send this cart in, no, that's not going to work. This one kind of stops, and the other one kind of goes. Go back and look at the video. Okay, so the first cart stops, and the second cart goes with the velocity of the first one. Let's calculate V2 final for the case where the two masses are equal and the collision is elastic. I have 2m1 over m1 plus m2 v1 initial. But m1 and m2 are the same, so it's just 2m1 over 2m1, which is just v1 initial. So when the carts have the same mass, the one that comes in comes to a stop, and the one that goes out with the velocity the first one had coming in. That's pretty much what we saw when I did the video with the carts. Right? So let's do the case where m1 is much, much less than m2. So if I have a supermassive object here and something comes in and they collide elastically, this guy's just going to basically bounce off and go back the other way, right? This is a BB hitting a bowling ball, right? The bowling ball may move a teeny tiny bit, but not very much. The BB's just going to bounce backward off it. So what we'd expect is if m1 is much, much less than m2, the final velocity of cart 1 will be essentially the negative of his initial velocity, and the final velocity of cart 2 will be close to 0, right? And so let's just look at that. If we say so if we start with that top equation, v1 final is equal to m1 minus m2 over m1 plus m2 v1 initial. Well, what's the value of this in the case where m1 is much, much less than m2? Like if this is 1 and this is 1,000 kilograms, right? And this is minus 999 over 1,001. This is essentially -1. To the extent that m1 is less than m2, this starts becoming -1. And so this is about negative v1 initial, which is what we expected it to do. It goes in, it hits something that's way too massive, and it just bounces backwards, right? Similarly, v2 final is equal to 2m1 over m1 plus m2 v1 initial. But this is a tiny number compared to this guy. So this is like, instead of being 1, this is like 2 over 1,001. This is a tiny number multiplied by that initial velocity is about 0. And so this is also what we expect to see. Finally, let's look at the case. This is the least clear one, I think. But let's look at the case where m1 is much, much greater than m2. Again, these are our formulas for elastic collisions where object 2 starts out at rest, and we get, so now we have a really supermassive object coming in, and it hits another object. And so what do you think happens to it? Well, if the bowling ball comes in and hits the BB, the bowling ball's velocity shouldn't change very much, right? And so in this case, V1 final is equal to M1 minus M2 over M1 plus M2 times V1 initial. Well, if that's like 1,000 and that's like 1, then it's 999 over 1,001, essentially 1. In other words, its velocity doesn't change very much before and after the collision. It's 99% of it or more, maybe, depending on how much more massive it is. And so that at least matches what we expect. And finally, we have to look at what happens to the BB, right? If it's a bowling ball hitting a BB, so V2 final, this is one that's maybe the trickiest. This is 2M1 over M1 plus M2, V1 initial. And since this is like 1,000 and this is like 1, this is like 2,000 over 1,001, this is about 2. So it goes away with twice the velocity it had initially. We could certainly argue that it would be going a lot fast. It would be going faster than if the bowling ball comes in and hits the BB is going to shoot out, right? And the only argument I can give you about why it should be a factor of 2 is you can say, well, look, if you looked at it the other way and said the BB hit the bowling ball instead of the bowling ball hitting the BB would be going, say, 10 meters per second this way and then 10 meters per second that way. So it would get a 20 meter per second change in this collision. And that's what this is saying. It's saying if this guy comes in at 10 meters per second, this guy goes out at 20 meters per second. And so you would get that change. Anyway, if you don't like that one, you should like all the rest of them. And so this is a special case of solutions for V2 initial equals 0. And if you have that and an elastic collision, you can solve for the final velocities. Otherwise, you have to go back to the previous slide and work out what the two equations give you for conservation of momentum and conservation of kinetic energy. So here's a elastic collisions problem. Cart M1 equals 1 kilogram is traveling at 4 meters per second and collides elastically with cart M2 equals 3 meters per second, which is at rest. What are the final velocities of the carts? And so we have M1 is equal to 1.0 kilograms and V1 initial is equal to 4 meters per second. M2 is equal to 3, sorry, this should be kilograms. Oops. Kilograms, and V2 initial equals 0. So this allows us to use our formulas for elastic collisions where we said V1 final is equal to M1 minus M2 over M1 plus M2, V1 initial. And so that's equal to 1 kilogram minus 3 kilograms over 1 kilogram plus 3 kilograms times 4 meters per second. And so that's equal to minus 2 kilograms over 4 kilograms times 4 meters per second, which is minus 2 meters per second. And so V1 final is equal to minus 2 meters per second. Similarly, we can say, look, V2 final is equal to 2M1 over M1 plus M2, V1 initial, which is equal to 2 times 1 kilogram over 1 kilogram plus 3 kilograms times 4 meters per second, which is equal to 2 meters per second. And so when one goes in at 4 meters per second, it bounces off and goes backwards at 2 meters per second, and the other one goes forwards at 2 meters per second. So this is an elastic collision, and so we should have KE final equals KE initial. And so we'll say for part B of this problem, if that was A, call that A, part B, show kinetic energy is conserved, which means show KE initial equals KE final. So now we've got to come back up to the top. Whoa, I'll leave that line there, right? And I'll say, look, KE initial equals KE1 initial plus KE2 initial is equal to 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared. And that's equal to 1/2 times 1 kilogram times 4 meters per second squared plus 1/2 times 3 kilograms times 0 meters per second squared. And so this guy is just 0 because this velocity is 0. 16 divided by 2 is 8, and so that's 8 joules. Right? And so the initial kinetic energy is 8 joules. Let's figure out what the final kinetic energy is, right? KE final equals 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. And if kinetic energy is conserved, these will come out the same, right? And so this is equal to 1/2 times 1 kilogram times 2 meters per second squared, right? Because that was the final velocity of cart 1. If you want, you can put a minus sign in there, but it doesn't matter because it's squared, right? Plus, because this guy came out with a negative initial velocity, right? And then this is 1/2 times 3 kilograms times 2 meters per second squared. And so that becomes 2 joules. So minus 2 squared is 4, divided by 2 is 2. 2 squared is 4, divided by 2 is 2, times 3 is 6, plus 6 joules is 8 joules. And so KE final is equal to KE initial is equal to 8 joules. And so it is elastic, E-L-A-S-T-I-C, which is what we expected. Relative velocity is conserved in elastic collisions. What that means is that the difference between the two velocities is going to be the same, or the absolute value of it. So we did a problem a few minutes ago where we said cart 1, so this is cart 1, his initial velocity was 4 meters per second. And he collided with another cart, cart 2. Cart 2's initial velocity, so this is V1 initial. See if I can do that better. V1 initial equals V2 initial equals 0. Relative velocity of these guys is 4 meters per second, right? When we solve this problem, this guy had a mass of 1 kilogram, this guy had a mass of 3 kilograms, so on. We got V2 final equals minus 2 meters per second. And this guy is that's V1 final. And V2 final was 2 meters per second. The relative velocity of these two guys is the same, or at least its absolute value. Cart 1 is going 4 meters per second relative to this guy. This guy's going 4 meters per second relative to this guy because he's going 2 this way and this guy's going 2 that way. And so the 4 is conserved, right? And so you can show this if you start out with just the conservation of momentum. P final equals P initial, or that becomes P1 final plus P2 final equals P1 initial plus P2 initial, right? And so if we write those out in their raw form, I get M1 V1 final plus M2 V2 final equals M1 V1 initial plus M2 V2 initial. And now I want to put the 1's on one side and the 2's on the other side. So I'm going to write this as M1 V1 final, and I'm going to subtract this guy over minus M1 V1 initial, and then I put this guy on the other side equals M2 V2 initial, that's this guy, minus that guy, M2 V2 final. All I've done is rearrange this, right? I started with conservation of momentum, I rearranged a little bit. Now I can factor out the m's, and I get m times V1 final minus V1 initial equals, sorry, that's M1, m2 times v2 initial minus v2 final. So this is an elastic collision. So we're going to store this equation for a second, right? Write that one down or something. You clean that up just a little bit. M1. Right. Now we're going to do the same thing for kinetic energy. We're going to say KE final equals KE initial, so that KE1 final plus KE2 final equals KE1 initial plus KE2 initial. And then I'm just going to write those things out. So I get 1/2 M1 V1 final squared, that's this guy, plus 1/2 M2 V2 final squared, that's this guy, equals 1/2 M1 V1 initial squared, that's this guy, plus 1/2 M2 V2 initial squared, that's this guy. So right away I can see all the halves in this equation cancel, right? I can multiply everybody by 2 and get that. And I'm going to do the same thing here that I did here. That's saying I'm going to move the 1's to one side and the 2's to the other side. So this one becomes M1 V1 final squared. Don't be afraid of a little algebra. It's not too bad. Minus M1 V1 initial squared equals M2 V2 initial squared. That's this guy minus this guy, M2 V2 final squared. And now, just like up here, I'm going to factor out the m, so I'm going to get M1 times V1 final squared minus V1 initial squared equals M2 times V2 initial squared minus V2 final squared. Right. And now I'm going to have to do a little tricky, maybe slightly tricky algebra here. So I'm going to say, look, a squared minus b squared, if I have something squared minus the other squared, if you remember, that's equal to a minus b times a plus b. You take the outer, the inner, and the cross one. So this is a squared plus ab minus minus b squared. And so, I'm sorry, that's a minus sign. This guy, a squared minus b squared, factors into this guy. And you should check that. It's these two multiplied by each other, and plus these two, plus these two, plus these two, and you get that, right? And so I'm going to write this as M1 times V1 final minus V1 initial times V1 final plus V1 initial equals M2 times V2 initial minus V2 final plus times V2 initial plus V2 final. So I've taken each of these things and just broken up that way and written them this way. And if you'll notice, this piece here is this piece here, and this piece here is this piece here. And since they're equal, I can cancel them. Bam and bam. And that leaves me this thing equals this thing. And so I'm going to write that up at the top here after I make a little eraser move. I get V1 final plus V1 initial equals V2 initial plus V2 final. And now I'm going to put the initials together and the finals together. And so I get V1 initial minus V2 initial equals V2 final minus V1 final. These are the relative velocities. The first one minus the second one initially equals the second one minus the first one finally. It's the 4 minus the 0 is equal to the 2 minus the negative 2. And so this gives you conservation of relative velocity. And so if you know it's an elastic collision, and you know the relative velocity at the beginning is 4 meters per second, you know it has to be 4 meters per second at the end. And so you can just use that. So two billiard balls approach one another. Ball one is traveling at 3 meters per second and ball 2 is traveling at minus 1 meter per second. What is their relative velocity, right? And so here's ball 1, and it's going v1 initial equals 3 meters per second. And here's ball 2, and this is v2 initial equals minus 1 meter per second because it's going the other way. And so the relative velocity, v rel, is equal to v1 initial minus v2 initial, right? The velocity of one relative to the other. If this one's going 3 that way and this one's going minus 1 that way, the relative velocity is 3 meters per second minus negative 1 meter per second, or 4 meters per second. We'll call that A, right? B. Assuming an elastic collision, what is the relative velocity after the collision? Right, and the answer is it's what we derived in the last problem, on the last video. We said, or earlier, we said v1 v1 initial, doesn't matter, minus v2 initial is equal to v2 final minus v1 final. This is the relative velocity after the collision. This is the relative velocity before the collision. It's actually got the 1 and the 2 in reverse order because this guy will be moving to the right faster than 1 will after the collision. This guy's moving to the right faster before the collision because that's why they collide. So if this is 4 meters per second, which we just determined up here, then this is also equal to 4 meters per second. And so the relative velocity after the collision is also 4 meters per second. Because it's an elastic collision. This is true for elastic collision.